In this video, we will have a look at aromatic chemistry studied in A-level chemistry, and I will do a quick overview of aromatic chemistry and going into a few details. This video should suffice when revising this topic. So first thing we look at benzene, and we look at the bonding and structure in benzene. So this is known as aromatic chemistry, looking at compounds which contain a benzene ring, and we will look at benzene ring in detail. So what is benzene first? It's a colorless liquid at room temperature. Its boiling point is much higher than hexane of slightly comparable molecular mass, because benzene is a ring structure that packs really well together, therefore increases the strength of van der Waals forces. It burns with a sooty flame, and it also undergoes combustion reaction. Few things on naming compounds, aromatic compounds. We will call this first one methylbenzene, chlorobenzene, and nitrobenzene. So you can see the derivatives that are added onto the benzene ring. Here are a few other names: nitrobenzene, bromobenzene, chlorobenzene, ethylbenzene, and you've got three isomers of methyl bromobenzene, and the naming is clear. I don't want to spend too much time on naming, so I'm more interested in the structure and I'm more interested in the reactions. Bit of history: benzene was first isolated by Faraday in 1825. Considered benzene to be like a linear structure with 4 double bonds, with a molecular formula of C6H6, empirical formula of CH, and molecular mass of 78. It was Kekulé who, it is said, that had a dream once that he saw a snake chasing its tail, and he came up with the cyclic structure of benzene. So now please look at benzene very, very carefully, and I will do a few annotations here. So benzene has alternate double bonds, 1, 2, 3. So that's the structure. At A level, we draw benzene. It's a cyclic one with a circle in the middle, and we will explain what this circle means later on. So Kekulé's structure had a few problems. Firstly, benzene has 3 double bonds, if we see here, but benzene does not decolorize bromine water. So if anything, benzene does not react in a similar manner to the reaction of alkenes with bromine water. So benzene undergoes electrophilic substitution reaction. So benzene has a lower reactivity than, say, cyclohexene. Second problem with Kekulé's structure was, Kekulé said dibromobenzene had 4 isotopes, but in reality 1,6 and 1,2 is exactly the same once we know the convention for naming compounds. So that was another problem with benzene. He suggested an equilibrium model. He said benzene has a resonance structure, and you can see with alternating double bonds, and that's one of the reasons why these problems occur. Again, it was in the early 1900s with the discovery of crystallography, X-ray crystallography, that we discovered that benzene is a perfectly cyclic structure. Now, we know this much. A double bond between 2 carbons has a bond length of 0.133 nanometers, and a single bond has a bond length of 0.154 nanometers. With the use of X-ray crystallography, it was discovered that benzene actually has a cyclic structure where all bond lengths, all of the carbon to carbon single and carbon to carbon double bonds are equal, and they have a bond length of 1.40 nanometers. So benzene is perfectly hexagonal, bond angles of 120. So that bond angle there, that bond angle there is 120. Let me change the color of the pen. Make it red or green. Okay, so look, that bond angle there is 120 degrees. Around each carbon, you've got a trigonal planar shape. So we know this. So now let's look at hydrogenation of benzene and stability of benzene. Benzene, cyclohexene, when cyclohexene undergoes hydrogenation, the amount of energy released is 120. So naturally, if we have calculase benzene, which we call cyclohexa 135 triene, this is also called hypothetical benzene. When that undergoes hydrogenation, that releases minus 360 kilojoules of energy per mole. However, when benzene undergoes hydrogenation, it releases minus 208 kilojoules per mole of energy. So let's place this on an energy level diagram or an enthalpy level diagram. So what do we notice? That cyclohexatriene releases minus 360 when joules per kilojoule when it is undergoing hydrogenation. Cyclohexene minus 120, and benzene is here. So you can see now benzene is more stable by the hexatriene by 152 kilojoules per mole. And this stability is something we will explain now. So that slide just explains to you, this is worth 4 marks in an exam. Now let's look at why benzene is more stable. What gives benzene the stability? Why is it lower than cyclohexatriene on an enthalpy level diagram? Why is benzene more stable by 152? Okay, right. And this is to do with what we call delocalization of benzene. Okay, what does this mean? So very quickly, let's draw benzene. That's benzene. And if we go back to the formation of a double bond, then we know carbon has an electronic configuration of 1s2, 2s2, 2p2. Normally, I would ask you to recap on the formation of a double bond or the nature of a double bond in alkenes. But just to keep this video short, to highlight what's going on here. Carbon forms 4 bonds. The 2s2 and the 2p2 electrons are used to form bonds. So 1 bond, 2 bond, 3 bond. It's got a hydrogen there. You can see each carbon. So that leaves us with a spare p orbital. These p orbitals will overlap sideways. So I'm just going to change the color of the pointer. So these p orbitals are going to overlap sideways like this. Okay, so overlap of p orbitals. That results in a, change the color, okay, that results in a cloud of, this cloud of pi electrons spread over 6 carbons, and we call this that the pi electrons are delocalized. And that's exactly what's happening here. Each carbon has 3 covalent bonds and 1 is bonded. So I'll erase what I've written here so you can see this easily. Okay, so you can see now pi electrons, the p orbitals are overlapping. That results in a cloud of pi electrons. This is a cloud of pi electrons spread over the ring, and we said the 4th electron of each carbon in a these p orbitals overlap and form a cloud of pi bond, which is pi electrons which are delocalized, spread over the ring, and this gives benzene its stability. So all you need to know is the delocalization of pi electrons over the 6 carbons gives benzene its stability. And you can just have a read of this, pause the slide here, read of this. What I would say is these are the last 3 bullet points which are worth reading. Okay, this overlap of produces pi bonds. Can you see the p orbital overlaps to form a cloud of pi electrons spread over the 6 carbons in the benzene ring, gives benzene its delocalization, and hence benzene is drawn like this with a circle in the middle. So now let's look at the reactions of benzene. Okay, due to the stability of the delocalized rings, benzene does not react like alkenes. Okay, so benzene undergoes electrophilic substitution reactions. So this is what I want to look at. The first reaction I want to look at is the nitration of benzene. So please note here the conditions, the reagents are concentrated nitric and concentrated sulfuric. Let's do the mechanism here. When you do the mechanism of benzene reaction, the first thing you have to do is you have to generate the electrophile. In this reaction, electrophile is generated from nitric acid reacting with concentrated sulfuric acid, which is your catalyst, that produces NO2 plus water plus HSO4 minus. So I've done this in one step. There's my electrophile. The next step will be the benzene. Is where I think I'm a bit too low on the okay. So I want to do the mechanism on this slide then. So get my pen again. Okay, so pen color, I'll use green. So here's my benzene ring. An arrow from the circle goes towards NO2 plus. That's step 1. Now this cloud or this circle will get disturbed into a shape of like a shoe horse horn with a positive in the intermediate. Because it's a substitution reaction, the electrophile will replace the hydrogen. So please note the bond between carbon and hydrogen will break, so the arrow goes into the ring back. That generates NO2 and H+. That's your mechanism. Simple as that. One more mechanism then. The rest you can read for yourself. The next mechanism is called Friedel-Crafts alkylation or acylation. This is where we can add an alkyl group and an acyl group to the benzene ring. And you can see this here. This R is coming from a halogenoalkane like CH3Cl. This part is coming from acyl chloride. In both reactions, aluminium chloride is your catalyst. So I'll do one reaction here, and I want to do this reaction between CH3 COCl that forms, we call this acylation, and HCl. So number 1, let's generate my electrophile E plus. CH3 COCl reacts with aluminium chloride to form CH3 CO plus AlCl4 minus. The next step is the mechanism, and then you can see there's no change, but I'm just going to show you just a different way of looking at this. There's my electrophile. So you can see from the ring, from the circle, an arrow towards the electrophile, and then in the next step your delocalized cloud gets disturbed, and I've drawn the shoe hose horn differently slightly because I want to add the electrophile on the top. Please note this horseshoe horn should not go beyond these two carbons here. Then an arrow from the hydrogen bond breaks, and there's your product and H+. This H+ can react with AlCl4- to regenerate your catalyst. Okay. Next one, there are uses for nitrated arenes used to make dynamite, and an important reactivity is that when you react cyclohexene with Br2, you get that happening. In the case of benzene, because benzene there is no area of high electron density, so benzene can't polarize bromine, which is nonpolar, hence it undergoes substitution reaction with the use of a catalyst. So hopefully that's a nice summary in about 17 minutes for you. Please have a read of this, go through your notes, go through the textbook pages to help you understand benzene in detail. This is a quick overview of benzene for you. So I hope you like this video.